You know, usually when we think about large-scale construction projects, things like highways or bridges or massive overpasses.
Right, the really disruptive stuff.
Yeah, exactly. There is this baked-in assumption that it is just going to be this long, totally chaotic process
Yeah.
of disrupting nature. You picture the bulldozers, the concrete pouring, endless detours, the noise.
A lot of heavy machinery.
It is. And the natural assumption is that the animal kingdom wants absolutely nothing to do with it. I mean, they scatter, they hide.
Which makes sense, yeah.
But then you look at what happened in California recently, up in Siskiyou County. They are building this massive wildlife overcrossing over State Route 97.
I saw this, yeah.
It's a bridge specifically designed for animals to safely cross a notoriously dangerous stretch of highway. And the incredible, like, almost delightful thing about this project is that the local mule deer didn't even wait for the construction crews to pack up and leave.
They were just ready to go.
Totally ready. Before the bridge was even fully completed, we were talking dirt still being graded, heavy equipment sitting right nearby camera traps caught these deer just confidently tiptoeing across the span.
That is amazing.
Right. Nature was so desperate for a safe corridor that these animals were essentially standing at the edge of the tree line, tapping their hooves, just waiting for us to get out of the way so they could use it.
It really paints a wonderful picture, and it encapsulates a massive paradigm shift happening in global infrastructure right now.
How so?
For the last century, human engineering has operated on a very simple premise, which is we pave the roads and nature either adapts to us or it dies.
Yeah, we just plow right through.
Exactly. But that moment with the mule deer on Route 97 represents something entirely different. It represents a moment where human beings are finally adapting our infrastructure to the biological realities of the natural world.
Which is exactly what we're getting into today. Welcome to today's deep dive. We are exploring the absolutely fascinating, rapidly expanding field of road ecology.
It's a great topic.
It really is. This is a branch of science completely dedicated to understanding how our massive human transportation networks fragment the natural world, and much more importantly, how we are actively re-engineering the planet to undo that damage.
And there is a lot of damage to undo.
Tons. We have pulled data from everywhere today to figure out how this actually works. We are synthesizing federal highway safety reports, deep in the weeds, ecological studies, global engineering dispatches from Europe and Asia.
And don't forget the financial analyses.
Oh, absolutely. We're tracking the billions of dollars being poured into these projects. And if you are stuck in traffic on the interstate right now or just commuting to work, you might be wondering why you should care about a bridge for a deer.
Right. Why does this matter to the average person?
Exactly. Because this isn't just a nice, feel-good environmental project. This is fundamentally about saving human lives. It is about preventing billions of dollars in property damage.
And ensuring the survival of entire ecosystems.
Yes, especially in the face of a rapidly changing climate. For most of us, a highway is just a convenience. It is how we get from point A to point B.
But to a mountain lion or an elk?
Yeah, or a migrating herd of pronghorn. That ribbon of asphalt is a lethal, impenetrable wall that completely reshapes their entire existence.
To truly grasp the solution here, we have to establish the sheer scale of the collision between human mobility and animal migration.
Let's look at the numbers.
When we look at the data, specifically tracing back to a really landmark Federal Highway Administration report to Congress regarding wildlife vehicle collision reduction, the numbers are staggering.
They really are.
We are talking about an estimated 1 to 2 million wildlife vehicle collisions annually just in the United States alone.
Millions every single year. That's just wild to think about.
And those are just the reported collisions, right?
Oh, right, because people don't always call it in.
Exactly. The actual number is likely much higher because many animals are struck and, well, they wander off the road before being documented.
That makes sense.
But even sticking to the official data, these collisions account for a massive percentage of all reported motor vehicle crashes. We are looking at hundreds of human fatalities, tens of thousands of severe injuries, and over $8 billion in economic costs annually.
$8 billion. With a B.
With a B. That includes vehicle damage, medical costs, towing, and the labor required to clear the roads.
So we have a crisis that is killing people, killing wildlife, and costing billions. Obviously, civil engineers have known about this for a long time.
Yes, it's not a new problem.
I have to imagine the initial reaction wasn't immediately, let's build a $50 million forest bridge. What did the early attempts to solve this look like?
Well, the initial reaction, particularly around the early 2000s, was to try and solve the problem with technology rather than heavy infrastructure.
Okay, technology. Like what?
There was a highly publicized attempt in 2002 that the media affectionately dubbed the Bullwinkle Defense System.
I appreciate any government program named after a cartoon moose.
Right. It definitely caught the public's attention. The system itself was essentially a complex array of infrared sensors and electronic warning signs placed along known wildlife corridors.
So like motion sensors, basically.
Yeah, the engineering logic was straightforward. When a large animal, like a moose or an elk, approached the shoulder of the highway, their body heat and movement would trip the infrared sensor.
How's that?
This would trigger a series of bright, flashing electronic signs down the highway, warning motorists to drastically reduce their speed because an animal was in the immediate vicinity.
I mean, on paper, that sounds perfectly logical. We use motion sensors for security lights. We use them for automatic doors. It is cheap. It is deployable. Why didn't it work?
It failed because it relied on two highly unpredictable variables interacting in real time.
Which are?
The erratic behavior of a wild animal and the reaction time of a human driver traveling at 70 miles an hour in the dark.
Yeah. That's a bad combo.
The sensors themselves were notoriously finicky. They could be triggered by heavy snowfall, blowing branches, or even flocks of birds, leading to constant false alarms.
So the signs would just be flashing all the time for no reason.
Exactly. And if the signs flash constantly for no reason, drivers develop alarm fatigue and they just start ignoring them.
Like a car alarm going off in a parking lot, eventually you just tune it out completely.
On the flip side, sometimes the system worked perfectly. An elk would approach the road, trigger the sensor, the sign would flash, and the driver would slam on their brakes.
But
the elk would just stand in the ditch eating grass with no intention of actually crossing.
oh, wow.
So you have a highway coming to a screeching, dangerous halt for literally no reason.
That sounds like a recipe for a pileup.
It is. Or you get the absolute worst case scenario. The animal is spooked. It bolts across the road at a full sprint and crosses the asphalt far too quickly for the driver to react.
Regardless of whether the sign was flashing or not.
Exactly. The technological approach revealed a fundamental truth in road ecology. You cannot manage animal movement with flashing lights and speed limits.
Wait, he'd something physical.
Yes. The only mathematically and biologically sound way to eliminate the danger is physical separation. You have to put the animals over the traffic or under the traffic.
Which brings us to the physical infrastructure, overpasses and underpasses. I want to look at the dual safety gains here, because the data on crash reduction is incredible.
It really is night and day.
Take Colorado's Greenland Wildlife Overpass on Interstate 25. This is a massive, arching structure. It spans a highly trafficked interstate, reconnecting thousands of acres of critical habitat specifically designed for large roaming animals like elk, mule deer, and pronghorn.
And the results were immediate.
Yeah. Once that physical separation was established, the collision data just plummeted. It is measurably saving human lives and preventing totaled vehicles.
What's fascinating here is that if we want to examine the international gold standard for this physical separation, we have to look at Banff National Park in Canada.
Oh, Banff is legendary for this.
It is. The Trans-Canada Highway is a major economic artery, but it cuts directly through the heart of the Canadian Rockies. For decades, it was basically a gauntlet for wildlife.
Really dangerous for them.
Extremely. Grizzly bears, gray wolves, cougars, and elk were being decimated by commercial trucking and tourist traffic. But over the last few decades, Parks Canada implemented one of the world's longest-running, most heavily scrutinized mitigation programs.
They built dozens of these structures, right?
Yeah.
Both overpasses and underpasses.
Over 40 of them, actually. And the resulting data is definitive. Collisions with large mammals dropped by over 80%.
80%? That's huge.
And for certain species like elk and deer, the reduction was over 96%.
Wow.
But there is a crucial mechanical detail to this success, heavily documented by researchers who spent years monitoring the Banff project. Crossing structures are virtually useless on their own.
Wait, what do you mean?
They must be paired with coordinated highway mitigation fencing.
Wait, explain the mechanism there. If I build a beautiful, wide, vegetated bridge in the middle of the forest, why wouldn't the animals just use it?
Because an animal operates on the path of least resistance. If you build a bridge at mile marker 10, but an elk is foraging at mile marker 12.
It's not going to walk 2 miles to use the crosswalk.
Exactly. That elk is not going to hike 2 miles out of its way to use your bridge. It will simply step onto the highway at mile marker 12.
Right.
The physical bridge is only the crossing point. The actual mechanism of safety is the 8-foot-high, deeply entrenched steel fencing that runs for miles along the highway on either side of the structure.
So it blocks them from the road entirely.
Yes. The fence prevents the animal from accessing the asphalt and essentially acts as a physical funnel, guiding the wildlife along the tree line until they are seamlessly deposited at the entrance of the overpass or underpass.
So it is a totally engineered landscape. The fence is the wall, and the bridge is the only door.
That's a perfect way to describe it.
Which completely reframes how road ecology views a highway. It stops treating the road as an immovable, absolute boundary and starts treating it as a permeable membrane.
Exactly.
We are deciding exactly where the membrane is solid and where we allow it to be porous.
And this brings up an interesting dual mandate. For the transportation departments funding these projects, the primary directive is always human safety and, maintaining the economic flow of traffic.
Keep the cars moving.
Right. But for the ecologists consulting on the projects, the mandate is biodiversity and habitat connectivity. Wildlife crossings are one of the rare public infrastructure projects where those two totally distinct, sometimes opposing goals are achieved simultaneously.
The win-win.
It really is. The human safety metric justifies the concrete and the steel, and the ecological metric dictates the soil, the vegetation, and the location.
That brings up a massive logistical question. If we have the data proving these crossings save human lives, save animal lives, and save millions of dollars in avoided accidents, why aren't they everywhere?
That's the billion-dollar question.
Why isn't every highway in the country just a continuous series of tunnels and bridges? We are talking about multi-million-dollar projects. You can't just guess. I imagine a civil engineer can't just walk out into the woods, look at a nice grove of trees and say, yeah, looks like a good spot for a badger to cross. Pour the concrete.
No, definitely not. The site selection process is intensely rigorous. It is not guesswork. It is high-level computation. We are looking at research published in major environmental management journals that explores algorithmic approaches and multivariate analysis to identify these optimal locations.
Okay, stop right there because I have to play the proxy for the listener here.
Good.
When I hear algorithms and multivariate analysis in a discussion about where a deer decides to go for a walk, my brain short-circuits a little bit. How do you turn biology into a math equation? What exactly is an algorithm doing in the woods?
That's fair. Let's break down the mechanism. Imagine a vast landscape cut in half by a highway. The algorithm maps that landscape as a network of nodes.
Nodes, like points on a map.
Exactly. A node might be a critical winter feeding ground on the north side of the highway, and another node might be an essential spring breeding pool on the south side.
Gotcha.
The algorithm takes the biological necessity of an animal moving between those two nodes and assigns it a mathematical weight.
Okay, so a highly important migration route gets a higher number in the computer.
Yes. Then, the algorithm layers in the cost variables. Building a bridge over a flat section of highway costs X. Building a bridge over a steep ravine costs Y.
Buying the private land adjacent to the highway costs Z.
Exactly. The algorithm runs thousands of simulations, weighing the biological value of reconnecting specific nodes against the financial and engineering costs of building it at those specific mile markers.
So it's crunching all these numbers to find the sweet spot.
Right. It calculates the mathematical maximum return on investment. It answers the question, where can we build the cheapest, most structurally sound bridge that reconnects the most critical biological nodes for the widest variety of species?
So it is essentially running a massive, multivariable simulation of animal movement versus construction budgets.
Precisely.
And we see this data synthesis happening globally.
Yeah.
There was a fascinating dispatch out of Costa Rica.
Oh, the Pinto study, yes.
Yeah. Researchers were looking to identify priority wildlife mitigation sites in the southwestern part of the country. They weren't just looking at one variable. They layered topographical maps, daily traffic volume metrics, satellite imagery of forest cover, and ground-level species density reports.
It's an incredible amount of data.
They stack all this data to pinpoint the exact optimal meter of asphalt that needed to be bypassed.
What's fascinating here is that mathematical modeling is only one half of the equation. This is where road ecology gets really interesting. You have to violently collide that clean algorithmic math with the messy, on-the-ground reality.
Because nature is messy.
Very messy. Because a computer model running in a sterile lab might not perfectly predict the behavioral quirks of a specific animal in a specific valley.
I have to push back on the heavy reliance on math anyway. Don't wild animals have a habit of completely ignoring our carefully calculated spreadsheets?
They absolutely do. Which perfectly brings up a massive study conducted in China.
Oh, I read this one.
Right. Researchers were tasked with designing wildlife crossings along a new desert expressway. The target species were wild, ungulate-hoofed animals like ibex, argali, and gazelles.
Okay.
The computer models might look at the topography and declare, this narrow valley is the shortest distance between the mountains. Put the underpass there.
Makes sense on paper. Shortest distance equals lowest cost.
But the researchers conducted exhaustive field surveys and relied heavily on local expert knowledge. And they discovered that while the valley was geographically the shortest route, the local argali sheep would never go near it.
Wait, why not?
Because the wind patterns in that specific valley swirl in a way that disguises the scent of predators.
Oh.
The animals instinctually avoid it. A topographical algorithm cannot factor in the scent of a snow leopard on the wind. That requires local biological ground truth.
That is so wild. We see a beautiful synthesis of that big data and local observation in the concept of crowdsourcing, too.
Yes, definitely.
The UC Davis Road Ecology Center created something called the California Roadkill Observation System. It is a grim name, but the mechanism is brilliant.
It's incredibly effective.
It uses public observations, everyday citizens with smartphones, reporting exactly where they see animal collisions, to map the actual hotspots.
It proves that citizen science can directly inform heavy infrastructure. If the multi-million-dollar algorithm suggests building a bridge at mile marker 20, but the crowdsourced citizen data shows that the animals are actually dying at mile marker 22.
You adjust the blueprints.
You adjust the blueprint.
The absolute best example of this synthesis is the mitigation project along U.S. Highway 93 in Montana. This highway cuts directly through the Flathead Indian Reservation.
That's a landmark project.
They built dozens of crossings there. Extensive fencing, massive underpasses, overpasses. But the crucial element that made it a success was the deep integration of tribal participation.
Right. The Confederated Salish and Kootenai tribes didn't just sign off on the project, they were instrumental in the planning.
They were heavily involved.
They integrated traditional ecological knowledge with modern civil engineering.
They didn't just look at where a computer said animals should cross based on a topographical map. They looked at where generations of human observation knew the animals actually moved.
They understood the landscape on a multi-generational scale.
Exactly.
Road ecology cannot just be about applying a sterile mathematical formula to the wilderness. It requires combining the processing power of big data with the irreplaceable value of indigenous participation, citizen science, and local field biology to create a truly holistic roadmap for intervention.
Okay, let's step back and look at the board. We have the computational math, we have the local knowledge, we know exactly where the animals desperately want to cross, and we know these structures unequivocally save human and animal lives.
We have all the pieces.
So what is the holdup? Why aren't we rolling out 1,000 of these projects tomorrow morning?
We hit the universal bottleneck of all public works. Funding.
Always comes down to money.
It always does. Moving from the theoretical beauty of ecological connectivity into the harsh bureaucratic reality of state and federal budgets.
I want to play devil's advocate here for a second. Let's say I am a taxpayer in a state that is struggling. Our schools need money, our hospitals are understaffed, our electrical grid is aging.
All very real concerns.
Right. And then I read in the local paper that the Department of Transportation wants to spend $90 million on a landscaped crosswalk for a mountain lion. How do you convince me, the skeptical taxpayer, that this is a responsible use of public funds?
You convince the taxpayer by showing them the brutal mathematics of inaction. We constantly talk about the massive upfront cost of building these structures. Millions, sometimes tens of millions of dollars for a single overpass.
That's a huge sticker shock.
But the data reveals a massive financial cost to not building them.
Let's dig into that return on investment, because there is a perfect case study for this in Wyoming, the Trappers Point Crossing System near Pinedale.
This is a legendary site in road ecology. The area intersects with the path of the pronghorn, which is an ancient migration corridor that these animals have used for thousands of years to move between their summer and winter ranges.
Incredible.
But U.S. Highway 191 cut right across that path.
And before the crossings were built, that stretch of highway was basically a slaughterhouse.
It was devastating. High-speed collisions were destroying the pronghorn population and causing massive property damage and human injury. So the state invested heavily. They built 2 massive overpasses, several underpasses, and miles of directional fencing.
To answer the skeptical taxpayer, what did the financial data show after the concrete dried?
Financial analyses, including extensive research evaluated by organizations like the Pew Charitable Trusts, demonstrated that over time, these specific investments pay for themselves.
Really? They completely pay for themselves.
Yes, when you calculate the average cost of a severe wildlife collision, you have to factor in the totaled vehicle, the emergency responder deployment, the hospital bills, the lost wages from human injury, and the cost of clearing the highway. It is an astronomical sum per crash.
That makes sense. It adds up fast.
By virtually eliminating those crashes at Trapper's Point, the amount of money saved by the public and the state eventually exceeds the cost of building and maintaining the bridges. It is the definition of preventative health care for highways. You spend $20 million today to save $50 million over the next 30 years.
Which explains the massive shift happening right now at the federal level. We are currently in an unprecedented era for road ecology funding in the United States.
A total boom.
A major catalyst for this boom is the Infrastructure Investment and Jobs Act, which established a landmark program explicitly called the Wildlife Crossings Pilot Program.
For decades, funding for these projects was totally piecemeal. A state might scrape together some surplus highway funds, or a private conservation group would have to raise millions in donations.
Just scraping by.
Yeah. But the federal pilot program completely changes the landscape by dedicating national transportation funding explicitly for reducing wildlife vehicle crashes.
The Federal Highway Administration data is very specific here. In 2023, they awarded the first major round of competitive grants, totaling $110 million.
And then just a year later, they announced another $125 million awarded to 16 different states.
That's huge. And this money isn't just a blank check for concrete. It is earmarked for the entire ecosystem of a project. It pays for the initial mapping, the environmental impact studies, the actual construction, and the crucial fencing we talked about.
It is a massive injection of capital, but federal grants are highly competitive and they are not infinite. To truly solve the problem nationwide, the states themselves are realizing they have to establish permanent internal funding mechanisms.
Right. Researchers have been tracking how states are attempting to foot the bill long-term. They are exploring a variety of legislative maneuvers, fuel taxes, special vehicle registration fees, municipal bonds, and dedicated legislative appropriations.
Utah is aggressively leading the pack here.
Yeah, Utah's doing great work.
They recently approved a massive $20 million appropriation specifically dedicated to wildlife crossing infrastructure, building on decades of successful work protecting their migrating deer and elk herds.
And Utah is setting a precedent. States like Colorado, Oregon, and Virginia are actively pursuing new state-level funding policies.
And in Nevada, which already boasts dozens of successful crossings for desert bighorn sheep and mule deer, advocates are heavily pushing the state legislature to establish a permanent, dedicated fund.
Why is a permanent fund so much better than just asking for money when a project comes up?
Because it allows transportation agencies to plan proactively. If a state knows it has a dedicated $5 million a year for wildlife crossings, they can integrate those structures into routine highway upgrades.
Oh, that makes sense.
If they are already widening a highway, they can pour the concrete for an underpass at the same time, which is exponentially cheaper than trying to retrofit a bridge over a highway 5 years later after a collision hotspot has already claimed lives.
But we also have to report impartially on the political realities of this funding, because securing tens of millions of dollars for ecological projects is rarely a universally praised event.
No, there is always friction.
A prime example of this tension is the Wallace-Annenberg Wildlife Crossing in California.
It is arguably the most famous wildlife crossing currently under construction in the world.
It is a staggering piece of engineering. A fully vegetated, massive bridge being built over the incredibly wide, incredibly busy Highway 101 in Southern California.
It's massive.
Its primary goal is to reconnect fragmented habitat for a severely isolated population of mountain lions in the Santa Monica Mountains.
And despite the undeniable ecological necessity of the project, it has faced intense political and public criticism.
People were not happy about the price tag.
No, it became a focal point in debates over taxpayer spending, facing scrutiny over its massive cost, approaching $100 million, and the immense scale of the engineering required to span one of the busiest freeways in the nation.
It perfectly demonstrates the ongoing tension inherent in all public infrastructure. You have the friction between a necessary large-scale ecological investment designed to prevent the localized extinction of a species and the rigorous, often contentious political debate over how public funds should be prioritized.
Exactly.
However, Despite the political scrutiny, construction is pushing forward toward a revised completion target. It proves that when the biological data and the private-public partnerships are strong enough, the infrastructure gets built.
Which leads to the next logical step. Assuming the federal grants are secured, the state legislature approves the budget, and the algorithms have pinpointed the exact mile marker.
What actually gets built?
Right. What does it look like?
Because an overpass in Southern California does not look like an underpass in the deserts of Kenya. The architectural designs vary wildly across the globe. They are dictated by the local topography, the specific animals they are trying to save, and the harsh constraints of human development.
Absolutely.
Let's compare two dramatically different philosophies, the European approach and the Asian approach.
This is where civil engineering meets evolutionary biology in truly fascinating ways. Let's start with Europe.
Okay, let's head to Europe.
Europe has a unique challenge because it boasts some of the densest, oldest road networks in the entire world. They have been industrializing, dividing, and paving their landscapes for centuries.
And centuries before cars even existed.
Right. Consequently, their approach to road ecology doesn't just focus on moving a single species across a single road. They focus heavily on massive, sweeping landscape connections. They build what they call ecoducts.
Ecoducts. And the Netherlands is the absolute pioneer of the ecoduct.
They really are.
There is a structure there called the Nadrabrug Zandery Krelu.
That's a mouthful.
It is. The scale of this thing is difficult to overstate. It is not just a bridge over a highway. It is a continuous, heavily forested corridor that spans a highway, a railway line, a business park, and a sports complex.
That's incredible.
It's essentially picking up an entire forest ecosystem, lifting it into the air and draping it over human civilization to reconnect natural habitats near Hilversum.
To support that level of vegetation, the engineering is phenomenal. You aren't just pouring a concrete slab. You have to design a structure capable of holding thousands of tons of soil.
Deep enough for trees, right?
Yes, deep enough to support the root systems of full-grown oak trees, while managing water drainage so the bridge doesn't collapse under its own weight during a rainstorm.
I read that the French and German governments have integrated a concept called ecological transparency into their national infrastructure planning. What exactly does that term mean? Does it just mean removing fences?
Ecological transparency is an engineering philosophy. It means that when you design a piece of infrastructure, whether it is a road, a rail line, or a canal, the baseline requirement is that the natural landscape must be able to see and flow through it.
Okay, so it's about flow.
It dictates that an animal should be able to look at a human structure and see a clear, unimpeded path to the other side. The goal of these European nations is to actively undo centuries of industrial fragmentation by weaving the landscape back together on a macro-continental level.
Okay, so that is the European ecoduct, model-wide, sprawling, heavily vegetated, targeting entire ecosystems. Contrast that with the Asian approach.
Completely different set of challenges.
Yeah, they often have to navigate extreme, hyper-dense urban environments, or they're designed to target highly specific, incredibly heavy megafauna.
A perfect example of navigating extreme urban density is the Ecolink at BKE in Singapore. Singapore is an island city-state. Space is at an absolute premium. It is highly urbanized.
Very crowded.
But they recognized that their Bukit Timah Expressway had completely severed two critical nature reserves.
So they didn't have the luxury of building a sprawling European ecoduct across open farmland.
No, not at all.
They had to build a fully forested bridge spanning a massive urban expressway in the middle of a metropolis. It is an ecological lifeline squeezed into a concrete jungle, designed to allow pangolins, snakes, and birds to cross safely without ever leaving the forest canopy.
And then you have the engineering challenges of targeting megafauna, particularly in India.
Tigers and elephants.
Yes. The Wildlife Institute of India has been doing incredible work designing underpasses along National Highway 44 in central India. These aren't just concrete culverts, they are massive, open-span underpasses designed specifically for tigers.
And in Bengaluru, camera traps recently documented elephants utilizing the city's first planted overpass to access Bannerghatta National Park.
That's a huge engineering feat.
I want to emphasize the engineering math here. Designing a bridge to accommodate the casual strolling way of an entire herd of elephants is an entirely different structural challenge than designing a bridge for a European badger.
Exactly. The structural load-bearing requirements are astronomical. But beyond the physical weight, road ecology requires a deep psychological understanding of the target species. You are essentially playing animal psychologist before you pour a single yard of concrete.
Give me an example of how animal psychology changes the blueprints.
Let's look at Costa Rica. Conservation organizations there aren't building heavy concrete overpasses. They are building canopy ropes and aerial bridges strung high above the roads.
Why?
Because the target species are arboreal animals, monkeys, and sloths. Their entire evolutionary defense mechanism is staying high in the trees. If you build a beautiful, safe concrete underpass on the ground, a sloth will never use it, because forcing them to descend to the forest floor makes them incredibly vulnerable to predators.
You have to build a crossing in the sky.
Yes, where they feel psychologically safe.
We see highly specific interventions in Australia, too. At the Compton Road crossing in Brisbane, they combined a vegetated bridge with underpasses and canopy ropes to cover all their bases.
That's a very comprehensive design.
But on the Gold Coast, they had a very specific problem with koalas. A koala might wander onto the highway, get spooked, and then get trapped against the very mitigation fencing designed to keep them safe.
Which totally defeats the purpose of the fence.
Right. So engineers installed specialized escape poles, essentially tall wooden posts placed right against the fence on the highway side. If a koala is trapped, their instinct is to climb. They climb the pole, get over the fence, and escape back into the forest.
It is brilliant, species-specific design. But perhaps the most striking example of how animal psychology dictates infrastructure comes from research conducted in Kenya.
Oh, this study was fascinating.
Researchers spent a massive amount of time monitoring how different wildlife utilized 41 different crossing structures, including railway underpasses in the Tsavo ecosystem.
And they found a massive split in how different animals viewed the exact same concrete tunnel, right?
A profound split. They found that carnivores, hyenas, and leopards readily utilized the underpasses, but large herbivores, specifically giraffes and certain antelope, completely avoided them.
Wait, why? If the tunnel is physically tall enough for a giraffe to walk through, why would they refuse?
Because you have to look at the tunnel through the eyes of a prey animal versus a predator.
Okay, I'm following.
A hyena is a denning animal. It is psychologically comfortable in enclosed, dark spaces. It views an underpass as a safe, protected route.
But a giraffe.
But a giraffe relies entirely on its sweeping line of sight to spot lions and predators in the tall grass. An underpass is a dark, enclosed space with a blocked line of sight. To a giraffe's evolutionary instinct, that tunnel isn't a shortcut. It is a deadly trap where a predator could be waiting in the shadows.
That is fascinating. An underpass that is perfectly safe, structurally sound, and highly utilized by a leopard is a complete failure for a giraffe, simply because the giraffe's brain tells it that losing its line of sight equals death.
Precisely.
So if your goal is to move giraffes, you can't build an underpass.
Yeah.
You have to build a massive, wide-open overpass where they can see the horizon the entire time.
You are designing for the visual and psychological needs of the animal, not just their physical dimensions.
We have spent a lot of time discussing multi-million-dollar infrastructure. Tiger underpasses in India, elephant overpasses, massive ecoducts spanning railways in the Netherlands, federal grants debated in state legislatures.
The big-ticket items.
Yeah, and these projects take years to plan, years to fund, and years to build. But what happens to the animals that are migrating tonight?
That's a very different problem.
What happens to the smallest animals whose entire yearly migration route might only be a few hundred yards, but involves crossing a lethal two-lane country road? They don't have 10 years to wait for a federal environmental impact study.
This is where we see the absolute most vital, immediate component of road ecology: grassroots community action. While the federal government is focused on interstates, local citizens are focused on their backyards. And this is predominantly highlighted by the amphibian dilemma, particularly in the American Northeast.
Let's explain the biology here because it sets the stage for the danger. Every spring, as the snow melts, amphibians, specifically various species of frogs and salamanders, must make a perilous migration to reach vernal pools.
Right, vernal pools.
Vernal pools are temporary depressions in the forest floor that fill with water in the spring and dry up in the late summer. Because they dry up, fish cannot survive in them.
And because there are no fish to eat the eggs, these temporary pools are the only safe places for amphibians to breed. But the amphibians spend their winters buried in the upland forests.
So they have to commute.
Yes. So on the first warm, rainy night of spring, instinct drives them out of the mud and they march toward the pools.
But over the last 50 years, we have paved roads right between the upland forests and the vernal pools.
Exactly. And the conditions of this migration create a perfect storm for mortality. The animals are small, they are slow-moving, and they only migrate at night during heavy rainstorms.
Driver visibility is virtually zero. You can barely see the yellow lines on the road in a heavy spring downpour, let alone a 4-inch salamander.
The mortality rates are catastrophic. Entire local populations, hundreds of amphibians that represent the entire breeding generation for that specific forest, can be completely wiped out in a single evening by just half a dozen passing cars.
So because the government isn't going to build a $20 million bridge for a wood frog, everyday people step in.
The volunteers are amazing.
The volunteer efforts are incredible. The Vermont Center for Eco Studies and various state programs in New York and New Jersey have mobilized locals who physically go out and assist these animals across the road. But the most vivid, organized example is the Salamander Crossing Brigades.
Organized by the Hare Center for Conservation Education in New Hampshire.
I want to paint the picture of this because it is deeply moving. You have entire communities of people, families, retirees, college students, voluntarily leaving their warm homes to stand in the freezing rain in the pitch black of a spring night.
It's dedication.
They're wearing high-visibility reflective vests, holding heavy flashlights, and they're literally walking up and down the slippery asphalt, picking up spotted salamanders and wood frogs, putting them in plastic buckets, and carrying them across the street. They are acting as human crossing guards for amphibians.
It is a profound display of local environmental stewardship, but from a scientific standpoint, one might ask, is this sustainable? Is carrying frogs in a bucket a long-term solution, or is it just a temporary Band-Aid on a permanent infrastructure problem?
Right. You can't rely on volunteers standing in the rain forever.
You can't. But the brilliant mechanism here is that the grassroots volunteerism is exactly what creates the permanent infrastructure. These volunteers are not just acting as crossing guards, they are acting as field biologists.
Because they're taking notes.
They're collecting vital, hyper-localized data.
They have clipboards out there in the rain.
Yes, they're recording exactly how many amphibians are crossing, what specific species they are finding, the exact time of the crossing, and precisely which 20-yard stretch of road is the deadliest hotspot.
That's brilliant.
This citizen science is crucial because a massive algorithmic model running topographical data in a university lab is never going to detect a microcorridor used by 100 salamanders on a random country road.
The volunteers are providing the ground truth data that the computers miss. And that data directly justifies the funding for permanent solutions.
A historic example of this transition from grassroots to infrastructure is the Henry Street salamander tunnels in Amherst, Massachusetts.
This was a pioneering effort in America.
It was. Local volunteers and advocates had spent years documenting the exact location and the massive scale of the salamander migration across Henry Street. Because they had rigorous, multi-year data proving the mortality rate and pinpointing the exact crossing zone, the town and conservation groups were able to justify the expense of a permanent engineering solution.
They didn't build a massive overpass. They built small, specialized tunnels, essentially slotted pipes beneath Henry Street, specifically designed for the spotted salamanders to crawl through safely.
It demonstrates the incredible scalability of road ecology. It ranges from a $50 million vegetated ecoduct spanning a commercial railway in the Netherlands all the way down to a few $1,000s for a 6-inch plastic pipe buried beneath a 2-lane road in Massachusetts.
And they both serve the exact same purpose.
Both structures exist because data, whether algorithmic or gathered by volunteers in the rain, proved that nature needed a way across.
Which brings us to the ultimate question of this entire deep dive. Whether it is a massive ecoduct in Europe, a tiger underpass in India, or a tiny tunnel for a frog in New England, what is the overarching ultimate goal?
The big picture.
Yeah. We've talked extensively about saving individual animal lives, and we've talked about the economics of preventing human car crashes. But the scientific consensus makes it clear that the ultimate goal is not just about a single deer surviving a single crossing on a Tuesday. It is about the existential long game.
If we connect this to the bigger picture, the foundational concept we're driving toward here is ecological connectivity. Over the last century, our roads have caused severe habitat fragmentation. They have taken vast, contiguous wildernesses and chopped them up into thousands of isolated, disconnected islands.
And to fight this fragmentation, organizations are looking at the map on a staggering scale. The Yellowstone to Yukon Conservation Initiative, often called Y2Y, is working to maintain and restore wildlife movement across the entire northern Rocky Mountains.
It's an incredibly ambitious project.
They aren't just looking at one highway. They are looking at a continental corridor stretching thousands of miles.
And why does that massive scale matter on a fundamental biological level? Because if an animal population is stuck on a fragmented island surrounded by highways, the primary threat to their survival isn't actually getting hit by a car.
It's not.
No. The ultimate existential threat is genetic isolation.
Explain the mechanism of genetic isolation, because this is where the biology gets terrifying for these species. Let's look back at the mountain lions in California. The ones in the Santa Cruz Mountains, near the Laurel Curve Crossing, and the population in the Santa Monica Mountains, near the new Wallace-Annenberg Crossing.
Mountain lions are apex predators. A single male mountain lion requires a massive home range, sometimes hundreds of square miles, to hunt and find mates. But because they are entirely boxed in by multi-lane high-speed freeways, they cannot disperse.
They're trapped.
The young males cannot leave the territory they were born in, and new lions from other territories cannot get in.
They are biologically trapped on an island of asphalt.
Exactly. And when a small population is trapped together for generations, they inevitably begin to inbreed. Inbreeding leads to a phenomenon known as inbreeding depression. The genetic diversity of the population plummets.
Which leads to defects, right?
Yes. Recessive genetic defects begin to physically manifest in the animals. Things like kinked tails or heart defects. Their reproductive rates drop, their immune systems weaken, and eventually the entire isolated population simply collapses and dies out.
So the bridges, these multi-million-dollar crossings we've been talking about, they aren't just crosswalks. They were literal genetic lifelines.
That's exactly what they are.
By allowing just one or two new mountain lions to safely cross the highway every year, you are physically injecting fresh DNA into an isolated population, saving them from genetic collapse.
And then you have to add the ultimate overriding multiplier to this entire equation of connectivity: climate change. Insights tracked by organizations like the Nature Conservancy point out a brutal reality. As the global climate change is bringing prolonged, severe droughts, drastically increasing the frequency and intensity of wildfires, and shifting vegetation patterns, wildlife must be able to move.
They have to shift their ranges to survive. If a valley becomes too hot or the water dries up, the herd has to migrate to higher elevations or cooler northern latitudes.
But if a major interstate highway blocks the only path to a new climate refuge, the species cannot migrate. They are trapped in an ecosystem that can no longer support them, and they face localized extinction.
I want to use an analogy to tie all of this together. Think of the natural world like a healthy human circulatory system. The vast forests and plains are the organs, and the animals moving between them are the blood, keeping the whole system alive and functioning.
I like that.
For the last 100 years, our highway system has acted like 1,000 tight rubber bands wrapped randomly around those veins. The blood can't flow, the wildlife can't move, and those isolated limbs, those fragmented islands of habitat, are starting to wither and die. Road ecology is the science of methodically cutting those rubber bands so the lifeblood of the ecosystem can actually circulate again.
That is an excellent way to conceptualize it. We are restoring the circulation of nature. This raises an important question: how do we make this permanent? And we are seeing federal policies slowly begin to recognize this imperative. Initiatives like the proposed Wildlife Corridors Conservation Act and the National Park Service's growing focus on designating national wildlife corridors signal a massive shift. The goal of road ecology is no longer merely damage control. It is proactive climate resilience.
We have to fundamentally integrate land conservation with transportation planning at the very inception of a project. We have to design the bridge before we lay the asphalt, rather than trying to retrofit a multi-million-dollar tunnel under a highway 50 years after the ecological damage is already done. The infrastructure of the past century divided nature. The infrastructure of our future must actively weave it back together.
We are entering an era where engineering is finally working in tandem with evolutionary biology.
We have covered an incredible amount of ground today. We started with the intense computational math, the algorithms and multivariate analyses used to pinpoint the exact optimal mile markers for crossings, and how that math must be checked by the ground truth reality of traditional ecological knowledge and citizen crowdsourcing.
We explored the shifting financial landscape, tracking the massive influx of federal grants and dedicated state funding, proving the economic reality that investing heavily in wildlife infrastructure is preventative healthcare that pays for itself by eliminating catastrophic collisions.
We compare the architectural marvels spanning the globe, from the sweeping, multi-use, heavily vegetated aqueducts of Europe designed for ecological transparency, to the hyper-specific urban designs of Asia, and the arboreal canopy ropes of Costa Rica. We learned that an underpass that feels like a safe den to a leopard looks like a deadly trap to a giraffe.
We stood in the freezing rain with the grassroots salamander brigades of New England, proving that hyperlocal community action can literally lay the groundwork for permanent municipal infrastructure.
And finally, we looked at the existential long game. How large-scale ecological connectivity is our absolute best defense against the quiet tragedy of genetic isolation and the looming chaotic threat of climate change.
It represents a profound shift in how humans choose to exist alongside the natural world.
But I want to leave you with a totally new concept to ponder, something that builds on everything we've unpacked today but looks a little further down the road. Early in the deep dive, we discussed the failed Bullwinkle defense system from 2002, the infrared sensors that tried to detect animals and trigger flashing signs to warn drivers.
Right, the flashing signs that didn't work.
It failed because the technology wasn't smart enough, and human drivers doing 70 miles an hour are far too unpredictable. But I want you to think about the near future of road ecology as our vehicles become entirely autonomous and our highways become fully smart.
Oh, that's an interesting angle.
Imagine a future, maybe just a decade or two away, where autonomous vehicles are communicating directly in real time with wildlife tracking collars via a localized digital grid.
That changes the paradigm completely.
Exactly. Imagine AI-powered smart highways that don't rely on a flashing yellow sign to grab a distracted human's attention. Instead, the exact second a herd of elk approaches the roadside, the highway's network dynamically and automatically lowers the speed limits of every autonomous car within a 2-mile radius.
So the cars do the work for us.
The cars seamlessly slow down, the animals cross safely, and the cars speed back up. We could be looking at a future where we turn our cars and our data networks into invisible digital wildlife crossings. The concrete bridges and the steel fences will always be vital for heavy interstates. But the future of road ecology might not just be what we build over the road, but how the road itself actively communicates with the wild.
That's an amazing thought to end on.
Thank you so much for joining us on this deep dive. The next time you are on a highway road trip, look out the window. Look at the overpasses, the tall fencing running along the tree lines, the culverts passing under the concrete. We hope you view that stretch of asphalt through an entirely new, ecologically connected lens. Until next time.